Okay, this is going to be our last fluids video, and we're going to spend this video focusing on something called Bernoulli's equation. Bernoulli's equation is a relationship between a number of factors, between pressure, density, elevation, and speed in some flowing fluid. And all the assumptions that we've made about fluids still work when we're dealing with flowing fluids like this. So I'm going to sketch out a picture. As you can see, what I've drawn here is a pipe, essentially. And the pipe is full of flowing fluid. We're going to say that down here we have an elevation of y equals 0 meters. Remember, we can set that pretty much wherever we want. Here we have YA, and up here we have YB. And we have two little sections of fluid that we're dealing with here, or at least we're going to show fluid in two different sections. Okay, here's fluid in this little section down here, which I'll call A, and here's an equal amount of fluid, equal volume, up here in a section that I'll call B. And what we're going to do is we're going to derive what Bernoulli's equation is. You might be like, well, where are we even supposed to start from? The neat thing about Bernoulli's equation is that it comes from the principle that you are very familiar with, the principle of the conservation of energy, okay, which we studied a lot last year. What we're going to do right now is work through the derivation so you can see where this particular equation comes from, because it's kind of a complex equation, and I don't just want to throw something at you and say, here, you're going to use this. Okay, so here's our derivation. To get the fluid from where it is at point A to where it is at point B, the volume of fluid shown must have work done on it. Which changes the fluid's kinetic energy. And this idea is represented by this equation. The total work done is equal to delta K. So there's a bunch of different forces that end up doing work on this fluid. First one we're going to talk about is the force of gravity. Force of gravity does work to bring the fluid up from where it starts off at a position of YA to a position of YB. The elevation increases. So let's talk about the work done by gravity. WG equals the force of gravity times, I'm going to do displacement in the Y direction, times cosine of theta. Force of gravity is mg, so this is m being the mass of the liquid, times g, times, let's see, the distance that an elevation that it gains is yb minus ya. And then, let's see, force of gravity points down, the displacement is up, so that means we're dealing with vectors that are opposite each other, which means there's 180 degrees between those vectors. The cosine of 180 degrees is -1. And I'm going to change this mass, the mass of the liquid. That's not really helpful. I want this not to be the mass of the liquid, but instead the density times the volume. Remember, we're just using that density equation there. So I'm going to put the negative out in front. density of the liquid times the volume of the liquid that I'm dealing with times G times YB minus YA. That is the amount of work that's done in order to get the amount of liquid from point A up to point B. Notice that it's negative. This means that energy is being lost. It's kind of like we're losing gravitational potential energy here. Okay, so energy is coming out. There's some other work done. So to move the volume of fluid at A completely out of its, no apostrophe there, initial position, the fluid behind it, because remember this is steady flow, the fluid behind it must do work on it. In other words, the fluid behind it must push on the fluid at A until it's completely moved out of its position right there over some distance. I'm just going to call it D. Okay? I'm going to call it dA. So in order for this amount of fluid to completely vacate, this fluid back here has to put a force on this much volume of fluid to completely move it out of its position. And that would be equal to the volume that it's moved, dA. Okay? And how are we going to represent this? The work done by A equals the applied, or the force at A multiplied by, let's see, the distance A, the displacement A, times cosine theta A. Since the force on A and the distance that A, or the displacement, are in the same direction, we know that this is eventually going to cross out and be 1. But before we get to that, remember that we don't really deal with forces as much as we deal with pressures and areas. So because of the relationship between pressure, force, and area, I'm going to take this force and I'm going to write it as the pressure at A multiplied by the cross-sectional area that that force applies to, basically the cross-sectional area of the tube, or the pipe at A, times the distance, or the displacement that is needed to completely move the volume A out of its position, times the cosine of 0 degrees, which we know is 1. And then I just want to draw your attention to this. The area of the pipe at A multiplied by the distance, or the displacement that this amount of water moves through in order to completely get moved out. Well, an area times a distance, that's a volume. So I'm going to write down the pressure at A times the volume of A, the volume that A has to move through, literally the volume of this amount of water. So that's another amount of work that's done. That is energy, it's positive, so that's energy flowing into the system. So third, in order for A to move up here, that means the whole rest of this water's got to shift to the right, which means the water at B, or the fluid at B, which has the same amount of volume as the fluid at A, has to completely leave that section. And how we're going to do this is a little tricky. We're going to apply Newton's third law here. The fluid at B is pushing on the fluid in front of it to get it out of the way so that it can move into that space, which means the fluid just ahead of B pushes with the same magnitude back on the fluid that is actually at B. So the volume of fluid does work. Before we had work being done to something, now it's doing work on the fluid ahead of it at B over a distance, really should say displacement, dB. Due to Newton's third law, the fluid ahead puts the same force back on the fluid at B. So the work done at B is equal to the force exerted on the fluid at B multiplied by the distance that that force is exerted for multiplied by cosine theta B. We're going to do similar things up here where I'm going to change this to the pressure at B multiplied by the area, the cross-sectional area at B, times the distance moved through at B, times the cosine of 180 degrees. Again, that's -1. Again, I have the cross-sectional area at B multiplied by the distance that the fluid needs to move to completely vacate where it is right now at volume B. So I have area times distance. Again, I'm going to stick that negative out front. That's going to be equal to PB times VB. So we see three different forces that are doing work on our system. And we're going to combine this into the first equation that we wrote down. The total work equals delta K. The total work done is equal to the work done by gravity plus the work done on the fluid at A plus the work done on the fluid at B. And that's equal to negative rho VG YB minus YA plus PA VA. I guess it doesn't really matter whether these are capital or not, but it does bother me when I switch back and forth between them, so I apologize. Minus PB VB equals delta K, which equals 1/2 times the mass of the fluid, the change in speed, times, since we're doing delta K, it's the difference in kinetic energy between the beginning and the end, and we know kinetic energy is 1/2 mv squared. So taking the 1/2 from both terms, we're left with this, VB squared minus VA squared. And a couple more algebraic steps. Negative rho V. Oh, well, okay, so here's what we're going to do. VA is just the volume at A. VB is the volume at B. We said those are the same. And this volume right here, well, wait a sec. We said that was the volume that we're bringing from here up to here. Well, if A and B are the same, then that volume is the same. So I'm going to get rid of the subscripts on the V's. Just write this as negative rho VG. I'm not going to get rid of all the subscripts, but just the ones on the volumes, because I know that all those volumes, I've been dealing with the same volume the entire time. I've set up my problem that way. Oops, that's not a rho. That's P A V minus PB V equals 1/2. I'm going to change that M using the density equation to rho V, big V for volume, VB squared minus VA squared. Notice now that I have a V in every single term, so guess what? Those cancel out, and I'm going to do some rearranging. This gives me negative rho G YB plus, because I have two negatives, rho G YA plus PA minus PB equals 1/2 rho VB squared minus 1/2 rho VA squared. And now all I'm going to do is I'm going to collect all the terms with an A in them on the left-hand side, all the terms with a B in them on the right-hand side. And what I get is this. The pressure at A plus rho times the acceleration due to gravity times the elevation at A plus 1/2 rho, the density, times the velocity of the flow speed at A squared equals the exact same thing on the other side, except instead of the A's, we have B's. So at point B. And this is known as Bernoulli's equation. You'll notice that it kind of looks like a conservation of energy statement, and that makes sense because it really is one. Okay, so Bernoulli's equation. We have terms for the pressure at the two different points, we have terms representing the elevation, and we have terms representing the speed. Okay, that is Bernoulli's equation. There are some simplifications that can be made to this in certain cases. So we're going to talk about those in our conclusion here. Okay, right there. Good. So our conclusion. If the pipe is the same size throughout, then the equation of continuity, which we talked about in the last video, for equation of continuity for volume flow rates shows if the area is the same, pipe is the same size throughout, that VA must be equal to VB. So those terms cancel. And we're left with this. PA plus rho GYA equals PB plus rho GYB. And if that's the case, higher elevations in the fluid lead to less pressure. In other words, if YA is big and these two sides have to be equal to each other, that means PA must be smaller since there's the same density and the same acceleration due to gravity at all points. Leads to less pressure as seen before. Another conclusion. If instead we have a pipe that is horizontal, then in that case, YA is equal to YB. And these terms cancel. So PA plus 1/2 rho VA squared equals PB plus 1/2 rho VB squared. And if this is the case, therefore, for the same reasoning as above, higher speeds in fluids lead to less pressure as well. There we go. So that's the basics of Bernoulli's equation. Okay, sorry, I knew you couldn't see that right at the end there. That's the basics of Bernoulli's equation. There's lots of examples, and really to understand Bernoulli's equation, you got to play around with it a little bit. So I'm going to have you guys do that. That's it for fluids. The next topic that I think I'll be talking about is thermodynamics. So if you have any questions, please don't hesitate to ask. And until then, have a nice day.